Swayam Prabha. Digital India. Educated India.
In this lecture, we'll be discussing the PID control, proportional, integral, and derivative control. In the last lecture, we discussed about the proportional and derivative control, and we have assumed that the disturbance, torque, or moment will be zero. So let me write in P or PD control system, we assumed the disturbing moment or torque to be zero. But in practical problem, in real life problems, we generally can't ignore the disturbance. There is always disturbance. Suppose the aircraft is flying, there can be wind disturbance, for example. So hence, let's assume there are some torque acting in the system, disturbing torque. Let's assume there is disturbing torque MD is there in the system along with PD control. So we'll take you to the motivation why you have to consider integral control. So here we'll be going with the PD control with disturbance. Let's see how it is happening. So the system we had for PD controlled, I y double dot equal to Kp Ry plus minus Kd y dot. So this is we already had, we derived it, how it came. And now we are adding let me say something about the response. Suppose we have some system and the system should follow this line. Let's assume this is my reference line R of t. In PD control, what you have observed it, the system can start with oscillation, and with time the oscillation will decay into it will decay to the reference signal. But at steady state, there can be some error. Steady state means if you have any kind of response, and if this is my, suppose R of t is the desired signal or the reference signal to be tracked, if my system is going like this, the system goes to some constant value after some time, and system stays there. For all future time, the system stays to that value. So from these two goes to from the origin to this time, it goes to the steady state. It is called transient behavior of the system. And once it reaches to the steady state value, it is called steady state behavior. steady state response, we can say steady state response. So let me write here, even after the oscillations dies out in the PD control system, there will be steady state error in the attitude. So this is the problem happens in the PD control system if there is a disturbance. Or I should not say even in the disturbance, there should be some issues like this will arise in the system. Now, how to tackle these issues? Let's work on it. Let's assume similar to before, the reference attitude R of t is constant. So in this situation, if it is constant R of t at steady state, as I said, it stays to some values. So R minus Y equal to error. So error will be there forever after the system reaches to the steady state behavior. So it means R is constant here. What I said, R is constant here. And if E is constant here to after steady state, so Y should be also constant. It cannot be varied. So at steady state, we can say Y dot and Y double dot goes to 0. That is quite obvious at steady state because Y should be constant at the time. So hence, based on this condition, let me write this equation number 1. Equation number 1, we can rewrite at this condition R minus Y plus TD equal to 0. Or we can write Kp E plus TD equal to 0. Or we can write E equal to minus TD by Kp. So this is the problem arises if you have disturbance in the system in PD controlled system. So which is non-zero. And if you plot graphically, if you see the response, how it is grows with time. So if you graphically, if you look graphically, so it will have something. This is my t, and this is E of t. So if you see the magnitude t d by k p, so something like this, it is constant, and we can say this is the error, this is the area basically, and this area we can write A equal to 0 to t e t tau. And let me define this as figure 1. So this will happen at steady state. This is the condition will arise. I would like to why integral terms should come into picture. So PD control, proportional derivative control, PD controlled system does not have memory. There is no memory in PD control system. And to provide the controller with capability of driving the error to zero in the presence of constant disturbance, we need to add an integral term in the control law. So let me write, to provide the controller with capability of driving error to zero in the presence of external disturbance in the aircraft attitude motion equation, an integral term is added to the control law. So we have to add an integral term like ki integration 0 to t e tau d tau, where ki is greater than 0. And this is basically we call integral constant. So hence the PID control. So because of this, our integral term is coming into the PD control system. Hence, the PID control law is given by U of t equal to Kp E of t plus Kd E dot of t plus Ki 0 to t E tau t tau. And the controller transfer function, we can write if you take the Laplace transform, it will have U of s equal to Kp E of s plus Kd s E of s plus Ki s of s. And from this, we can write E of s divided by E of s equal to Kp plus s Kd plus Ki, should be Ki s. So this is basically, we can say this of s. And if you see the closed loop control structure, we have reference signal R of s. We have error from this summing point. We have controller here, Kp plus s Kd plus Ki divided by s. And the output from this block, we can write U of s. And if also we are having the disturbance, the system, so we have MDS, and we can write our attitude motion equation. We can write 1 upon I s squared. This is my GP of s equal to, this is my Y of s. This is the periodic feedback system. This summing point. So this is the system look like, or system, closed loop control system with PID control. Now, let me write a note here. How this integral term going to dissipate this term? How it is going to dissipate this term? So let me write one note here. It's a very important note. The integral term has memory that is it is proportional to the area under the error curve. This is my area, error curve area A. So now, if the error is non-zero, the integral term keeps on increasing to a larger value as to provide the correcting torque to the system. Until the disturbance torque has been compensated and the attitude error of the aircraft system which is R minus Y is to 0. Also, we can write here the integral term learns what disturbance torque in the system. Also, the integral term in the PID control learns what the disturbance torque acting in the system is. So this is a very, very important note why we need to consider the integral term in PID control. This is in this motivation we'll be moving in this course that control design, and this three type of control will be considering for designing the autopilot for the different systems or different equation of motions we'll be considering. Now let's look how we can modify the system response. As I mentioned that for any kind of response, we can have a two component. One is transient response, another is the steady state response. So suppose this is my y of t, and this is t-axis. So now, if our desired value somewhere is here, and if the response, aircraft response, attitude response, for example, is something like this, and after some time it gets settled here, for example. Now the question is how we can reduce this overshoot or undershoot, how we can reduce this steady state error. So there is we'll define some kind of parameters which will help us to modify the entire response. So here you can say before the system goes to steady state, we can say this is the part of the transient response. And once it reaches to the steady state, we can say, and after that time, we can say this is the steady state response. Now we have to design the controller in such a way that we can improve transient response as well as the steady state response. Now, how we'll be designing the controller precisely so that our mission objective is met? So here, the first and foremost part is the controller must provide asymptotic stability. So we have to design the controller. So objective is we need to design the controller in such a way that the controller must provide asymptotic to the closed loop system. If you refer the equation or the transfer function which relates between the input and output, reference signal and actual output, we had y of s equal to Cp of s, Gc of s, 1 plus Gp of s and Gc of s and Rs. So Rs is the reference signal and Ys is the actual output from the system. So the asymptotically stability means asymptotic stability means if you take the Laplace transform of this equation, y of t, we can write Laplace, not Laplace transform, inverse Laplace transform of this equation. Then we can write Gp of s, Gc of s, 1 plus Gp of s, Gc of s. So if you notice in this equation, the system has been transformed into time domain from the frequency domain. Now, we need to come up with some kind of specification which will help us to system to follow asymptotic stability. So here asymptotic means this expression, let me write this equation number 1, for example, must asymptotically go to 0. So this means the pole of this system must lie in the negative real axis. So I should say this means the poles of the characteristic equation 1 plus Gp of s, Gc of s equal to 0 must have negative real parts. So the poles should lies in this region, in the negative side. It may have a complex conjugate part, but it should have negative real part. That is very important. Now we have to come up with some kind of specification which will help us to modify our response. So as I said, we need to modify this response, how I can reduce the steady state error here, or how I can reduce the overshoot, undershoot. So we need to come up with some kind of specification which will help us to do this. And this is called the time domain specification. Time domain specification. What does it mean? So we are working till now on the Laplace transform, right? I mean the transfer functions, which are we have arrived in terms of Laplace domain. Now we need to convert it to time domain from the Laplace domain to time domain by taking the inverse Laplace transform, and based on in the time domain equation, we'll specify some terms which will help us to do our job. And this part is very, very important. How can modify the transient response and steady state response of the system. And let's continue on this part from the next lecture. Let's stop it here.